This tutorial demonstrates the regression method of hierarchical multiple linear regression. This problem can be found beginning on page 125 of the IBM SPSS for Intermediate Statistics book. The problem states, if we control for gender differences in math achievement, do any of the other variables significantly add anything to the prediction over and above what gender contributes? To solve this problem, we are going to use the hierarchical multiple linear regression approach. So how did I decide on the appropriate inferential statistic to use? Well, the SPSS book clearly indicated which statistical analysis to run. If we weren't given this information, however, we could use the following chart to dissect the problem and determine which statistical tests to conduct. This chart is located on page 86 of the SPSS book. Question 1 asks, how many variables are there in your research question or hypothesis? We have 3 or more, so we are going to follow this line to the next question that asks, how many dependent variables are there? We are looking at one dependent variable, which is math achievement. So the next question asks, is the dependent variable normal or scale? If we go to the data set and click on the variable view tab and find math achievement in our data set, we can see that it is scale. Going back to the chart we were just looking at, when it asks, is the dependent variable normal or scale, we will say yes. So we're going to follow our line once more to box 6, which says to use table 5.4 of the top row if the independent variables are normal or scale. This chart is found on page 90 of the SPSS book. Using the top row as indicated by the chart, we can see that we are looking at our dependent variable or variable outcome first, and we are looking at one dependent variable, so we are going to use this row right here. And then looking at the choices at the top, all of our independent variables are normal or scale, so we will be performing multiple regression. To determine the type of multiple regression method that we need to use, we need to look back at our question. So aside from gender, the other independent variables being referenced in this particular problem are motivation, grades in high school, parents' education, and math courses taken. We're interested in controlling for gender differences in this problem, which means we're interested in eliminating the effects of gender to determine the extent that the other variables predict math achievement. We won't be able to use a standard regression approach for this problem because all the variables or predictors in a standard regression approach are treated equally. We would not be able to predict the usefulness of each variable while controlling for a single variable. Therefore, for this particular problem, we are going to use the hierarchical approach. When running any type of multiple regression, the first thing that we're going to have to do is screen our data for violations of assumptions. One of the violations that we're going to have to screen for is homoscedasticity of the variance, which requires that the variance of error terms are similar across the independent variables. And we can determine that by looking at the scatterplot. The next violation of assumption that we're going to have to look at is to determine the linear relationship of the variables. And that's the relationship between each of the predictor variables and the dependent variable, and we want to make sure that it's linear. And we can also do that by looking at the scatterplot or a matrix scatterplot. And the last violation of assumption that we're going to look at is the multivariate normality. And we look at the p-plot of the residuals to determine that the error or the residual is normally distributed and uncorrelated with the predictor variables. We also have to make sure that our data meets the conditions of multiple linear regression to be able to generalize our data across a population, the first thing that we have to do is make sure that the dependent variable should be interval or scale, which we've already determined that it is, and normally distributed in the population from which it is drawn. The second thing that we have to do is make sure that our independent variables are mostly interval or scale, in which we have already determined, and there should also be no issues of multicollinearity. The first thing we're going to do is open our data set. We're using the HSB data new data set. Then we're going to check our assumptions first before we run our multiple regression by creating a scatter plot to check for linearity of variables. To do this, we are going to click Graphs, Legacy Dialogs, Scatter Dot. We're going to select Matrix Scatter and click on Define. Then we are going to move our variables over to this matrix box variables. We're going to move motivation, grades in high school, parents' education, gender, and math courses taken. And math achievement. These are all the variables that we are working with. We're going to click Options and make sure that Exclude Cases Listwise is chosen. Click Continue. And then we're going to click OK. So here's the scatter plot that we created. And what we're looking for is we're trying to make sure that the independent variables are linearly related to our dependent variable of math achievement. So if we look at math achievement here, we are looking at how this relates to all of our other variables. And if we look at all of our other variables in this column, we can see how it relates. We don't really need to worry about how the other variables are relating. And if we look in each of these boxes, we're looking just to make sure that none of those dots form a curve. We want them to be in a straight line or have no pattern at all. So we can see from looking at all of these boxes that none of them have any type of pattern or form a curve of any kind. So the scatter plot shows that the independent variables are generally linearly related to the dependent variable of math achievement, and that assumption has been met. Now we're ready to run our hierarchical regression, and we will check for the rest of the assumptions with the analysis of this regression. So the first thing that we're going to do is click Analyze, Regression, Linear. And if you already have variables right here, you can press this reset button right here and clear them out quickly instead of doing it one at a time. We're going to select math achievement because that is our dependent variable and put it there. And then next we are going to choose our independent variables, gender, and since we are doing this in an hierarchical fashion, we are not going to include the other independent variables because we want to analyze them differently than gender. So we're going to make sure this method box says enter, and then we're going to press next. Now we can input the remaining variables, which are motivation, I can find it, grades in high school, parents' education, and math courses taken. Then we're going to click Statistics, make sure Estimates is checked, Model Fit, Descriptives, Part and Partial Correlations, Collinearity Diagnostics, R-squared change, and confidence intervals. Press Continue. And plots. Normal probability plot. Continue. And we are going to press OK to run our regression analysis. The first thing that we're going to do with our regression analysis data is to check our assumptions, the rest of our assumptions, and to make sure that it meets the conditions for multiple regression. To check for multicollinearity, we are going to look at both the coefficients table and the model summary table, which I've provided for you right here. Our tolerance in the coefficients table, which will be this column right here, should be greater than 1 minus r squared. If we look at our model summary table, we can see where r squared is. And we can determine in this case that our tolerances should be greater than 1 minus 0.65, which is equal to 0.35. So all the values in that tolerance column should be higher than 0.35, and they are in fact all higher than 0.35, meaning that multicollinearity is not an issue with our data. The significance column indicates that the only variable that is significantly related to math achievement is math courses taken. And that is shown in this column right here, and we can see that math courses taken is the only one that is significant. The partial correlation values, which are located in this column, when squared, indicate the amount of unique variance in the outcome variable, which is math achievement, which is predicted by each independent variable. And when we square all of those values, we can see that math courses taken explains the most unique variance at 60%. The next chart that we're going to look at is our scatter plot. Now, because the dots are mostly scattered throughout the chart, it indicates that our data meets the assumption of the errors being normally distributed and the variance of the residuals being constant. The scatter plot also meets the assumption of homoscedasticity of variance because the dots on the y-axis are equally distributed across the x-axis. In other words, the values aren't distributed more to the left or to the right side of the scatter plot. This is an example of data that would violate the assumption of a homogeneous variance. This scatter plot shows that the variance of the y-scores tend to be low for small values of x and high for large values of x. This plot can be found on page 270 of the Applied Statistics book, which will be referenced at the end of this PowerPoint. Visual examination of our p-plot indicates some areas of possible concern because these dots don't exactly follow this line, but we can assume still, because they are close enough, normality of the residuals based on the p-plot. All right, now that we have determined that all of our assumptions are met, we will look at the rest of the output results to answer the problem. The first chart we're looking at right here is the variables entered or removed. We have Model 1 and Model 2 listed right here. This indicates that we first tested for gender as a predictor of math achievement, and then we added the remaining variables, which are listed right here, and tested that model as well. Going back to the model summary table, we have 3 new pieces of information that weren't included in the standard regression from the last problem. First is the R-squared change, which is right here. This test tells us how much the R-squared increased when we added the new predictors in Model 2. The F change and significance of the F change for Model 2 are going to tell us whether that change is statistically significant. In other words, whether adding the variables that we added in Model 2 to gender significantly improved on the first model that only had gender as a predictor. We can see that the additional variables improved on Model 1 using gender alone at 9% of the variance to explaining about 56% of the additional variance. We can also see that this is statistically significant change looking at the significant F change column, which shows that our result was statistically significant. The F change, therefore, is statistically significant and is written as F for 67, found here and here, equal to 27.23, went off the board. P.001, which I'm going to provide at the end in the results section again. One thing that's important to note here is that the R-squared change is based on the unadjusted R-squared, which doesn't adjust for the fact that there are more variables or predictors. So the other thing that we can look at then is the adjusted R-squared, the original adjusted R-squared for each model. And this will show us if there was still an increase even after we added the rest of those variables. So if we look at the adjusted R-squared for Model 1 and Model 2, which are shown right here, we can see that Model 2 is still better than Model 1 based on the large increase in the adjusted R-squared value from 0.08 to 0.63. Another table that we can look at to see that Model 2 is statistically significant is the ANOVA table. We would not be able to use this by itself. However, in determining whether the second model significantly improved on the first model, because it is possible for the second model to be significant without improving on the first model. That's why we looked at both the adjusted R-squared in conjunction with this result. Another thing that the ANOVA table shows us is that when gender is entered by itself, it is a significant predictor of math achievement. And that is seen right here. However, looking at the coefficients table and looking at the significance that gender has from being by itself, then when it's added to the other variables, we now see that gender is no longer a significant predictor of math achievement when all of the variables are included. This means that our previous simultaneous regression results, as found on page 124 of the SPSS book, that indicated that boys were apparent superiority over girls in math achievement, can no longer be completely explained by these other predictors. The next column that we want to look at on the coefficients chart is the standard coefficients column, the beta weights. The beta weights can help us in making comparisons among the predictors that we put in or the variables to see how much each one is contributing to predicting math achievement. That would be this column right here. With this combination of predictors, math courses taken has the highest beta at 0.68. And it's also the only variable that contributes significantly to predicting math achievement. None of the other variables are statistically significant. Based on what we reported earlier about the results of our research question, we can make the following statements in our results. To investigate how well grades in high school, motivation, parents' education, and math courses taken predict math achievement test scores, after controlling for gender, an hierarchical linear regression was computed. Assumptions were checked and met. Means and standard deviations are presented in the table below. I won't read all the information on the slides since we went over how we arrived at these results previously, but this is how we would write our outputs. The most important thing to note about this slide that we haven't already covered is the format of the chart that is on here. Overall, from this data, we see that the combination of the predictors when predicting math achievement indicates that math courses taken has the highest beta at 0.68, and it's also the only variable that contributes significantly to predicting math achievement. All right, now that we have finished reporting our results, that concludes this tutorial.